Hi, this is a project that I'm referring to as my Nixie Tube Filadometer. You may have seen Nixie Tube clocks, but this is actually a Nixie Tube filament meter. So the first line is the amount of filament extruded, and the second line is the percentage complete in the print. So the first line is in meters, so right now we have extruded 0.87 meters of filament. You'll see it kind of flicker back and forth in the last digit occasionally. I think that's when it's undergoing a retraction. So what are Nixie tubes? So Nixie tubes are gas-filled glass display tubes. It's similar to vacuum tube technology. Dates back to the late 50s, early 60s or so. These are very popular in clocks. Each one of these tubes has 10 different plates in it for the digits 0 through 9, as well as a little dot there for a decimal point. And the way it works is you supply 170 volts to the anode, and you ground one of these 10 plates, and it will light that particular digit. There's actually a mixture of neon and some other gases inside. So inside of this is a high voltage power supply and a Raspberry Pi. So this project was originally a indoor-outdoor thermometer. I actually built it about 6 years ago. Used to be mounted in this laser printed glued together case. It used to have one of these very old Raspberry Pi, original Raspberry Pi Model Bs powering it. It's the old style one. Hadn't used it in some time, so I decided to repurpose it for this particular project. So it actually has a Raspberry Pi 0W inside the case, and that is how it is getting its updates from Octoprint over Wi-Fi. Inside Octoprint I have a Prometheus endpoint that I use for another project. So this simply queries the Prometheus endpoint every so often, pulling the current data. The data it's looking at is the percentage complete and the extrusion amount. Now I could have put various other kinds of data. For example, it would have been relatively simple to display temperatures on this. I could have displayed hot end temperature and bed temperature. It'd be easy to display something like minutes remaining. Just about any parameter that you could pull from Octoprint could be displayed on a display like this. It's actually powered by an independent 12-volt power supply. The whole thing is completely independent of the printer. I did that because I didn't want any chance of my 170-volt power supply somehow backfeeding into the Octoprint server and killing something, so it's completely independent and talks to it over wireless. These are actually IN12 Nixie tubes, and this percent tube down here is an IN15. Here is one of the Nixie tubes themselves. You can see they've got little pins on the back, and they plug into a socket, so you can actually unsocket those and replace them if you need to. I 3D printed the case for it on this very printer. It's got a little snap-on bracket that mounts it down here to the top of the frame. Okay, let's take a look inside. Here you can see this circuit board. We've got the Nixie tube drivers here, and these 4 chips here, and then up here. I believe those are K155D chips. Also the same as the 74141. Then we've got shift registers here, 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 and here. I went with surface mount shift registers just because of room. Back when I built this many years ago, I was trying to get it to fit in a certain size case. Of course, we've got the Nixie tubes. There's a couple filtering capacitors, about 4 of them around. There's dropping resistors. And down here is a connector for the Raspberry Pi. Now we can unplug our Pi 0W. Originally I had this board set up for this Raspberry Pi. It was maybe Model 1 or whatever it was back in the day. So here's the back side of the board, so you can see some crud here. That was actually, at one point I had double-face tape sitting between the circuit and the Raspberry Pi, the shield over the USB connectors to insulate it, and there's still some gunk there stuck from the double-face tape. And then this daughter board here is the power supply. Okay, let's take a quick look at the schematic. I've done so many Nixie Tube projects and they're all quite similar that I'm not going to really spend a lot of detail on this, but I'll go over the key aspects. So I'm showing the first 4 tubes here, 1, 2, 3, and 4. Each tube is driven by an anode and 10 cathodes. So the anode is here, it has this resistor, which is a current dropping resistor, and then goes to a high voltage supply. High voltage supply, if memory serves, is in the neighborhood of about 170 volts. So the high voltage comes in through that resistor. Then you ground one of these 10 cathodes to make a digit light on the tube. To drive these cathodes, we have a 74141 driver chip. It's also known as the K155D. You can find the K155D readily available on eBay. Very popular chip for driving Nixie tubes. It drives them using binary coded decimal. So there's 4 bits to BCD. There is a 1s, a 2s, a 4s, and an 8s. So you add up those bits. So for example, if you wanted the number 3, you would add up the 1 and the 2. If you wanted the number 5, you'd add the 1 and the 4. That's BCD. So you might note that with these 4 pins, you can actually supply a value from 0 to 15, but there's only 10 outputs. So if you give this a value greater than 9, then it's either going to leave the display blank, or in some cases have an undefined out, lighting 2 different segments at the same time, something like that. The second 4 displays are exactly the same, 1 chip and 1 display for each one. Total of 8 displays with 4 bits each is 32 bits. Now there are different ways people will do this in their projects. A lot of people will use a multiplexed approach where you only light some of the digits some of the time. So you might light the odd digits and then light the even digits. And then you'd have a loop in your program that lights them alternately like that. And they do that so they can use half as many driver chips or a fourth as many driver chips. For me, I like the simplicity of the 1 driver chip per display approach, because once you put values on these lines, you can just set them and forget them. Now, you don't actually want to use 32 bits of I/O on the Raspberry Pi. In particular, I was using a Raspberry Pi Model B, the original B at this point in time. There was not 32 bits of digital I/O available. I don't even know if there's a full 32 bits on the current Raspberry Pis. But to get the number of lines to the Pi down to a reasonable number, use something called a shift register. And there are 4 of these shift registers over here. This is a 74595. And each shift register has 8 outputs, so 4 times 8 is 32, enough to drive all of our displays. And shift registers are inherently serial to parallel devices. There's inputs over here that come from the Pi. There's a data and a clock. What you'll do is you'll shift 32 bits into this. So you'll put your bit on the data line, and then you will pulse the clock line. That will load that bit. Then you do it the same with the next bit. Do that a total of 32 times. You'll load up all 4 of those shift registers. Once you get the data you want in the shift registers, you strobe the latch pin, and that tells it to take the data that is stored internally and make it live on the outputs. So using those 3 lines, the Raspberry Pi can control all 8 of these displays. Down here is the Raspberry Pi header. You can see I have the 3 lines going there to GPIO pins, and I also have a 5 volt and a ground hooked up to the header. The high voltage supply daughter board, I think I've covered this high voltage supply in some of my other videos. It's the same supply I use on all of my high voltage projects. I found it in a Nixie Tube kit that I built long ago, and I've been using it ever since. It's based on the TL494. I think you can probably find this mostly straight out of the TL494 datasheet. So we've got TL94, the TL494 is your regulator chip. It's going to drive a MOSFET, which is going to switch an inductor. There's a diode, and there is a capacitor. That's your basic boost converter circuit. You also have some feedback coming back through this 910K resistor into a potentiometer, and that tells the chip how much voltage you want in your output. So the chip, runs in a continuous loop comparing the feedback that comes from this resistor divider, through the pot, to an internal reference. And when your feedback is above that internal reference, it disables the output. When it's below, it enables it, and that's how it regulates its voltage. There's also some other stuff on here. For example, there's some filtering capacitors in the input. There's some transistor here that's used as part of the MOSFET driver. External resistors, capacitors needed by the regulator. I'm not going to go into detail on all of that. I don't even remember it all right now. If you look in the data sheet for the TL494, you will get all of that information. Okay, here we are a little bit later in the printing process. We're up to 8.29 meters of filament extruded, and we're 59% complete. The printer's just been humming along. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.